Okay, hello everyone. Thank you for the nice invitation. Thank you for the introduction. It's a pleasure to be here. A pleasure also to be among friends, Luca, Daniele, Sanya, and so on. So today I'm going to talk about active network alignment. So this is a work that is mainly forms a part of the PhD thesis of one of my PhD students who graduated last spring, and now he's in Google Research in Zurich. So this is the work of Eric Malmi. So as Sanya already said, I work in Aalto University. So I'm leading a group on data mining and graph mining. Our kind of research agenda is to do application-driven work on graph mining and social networks. We try to combine theory and practice, and some of the problems we are working are on finding dense subgraphs or networks, mining evolving networks and networks with labels, network alignment related to what I will talk today, and network inference. Also lots of work on opinion formation and influence propagation in social networks, which is currently some of our focus. And with respect to applications, in the past and not so much currently, but in the recent past, we have been working a lot on urban informatics and understanding cities and different applications. So this is something I'm also excited to talk with people here. And currently the focus has been shifting more on social network analysis, polarization, and maximizing diversity on social networks and so on. Okay, so let's start with the topic of the talk today. So the problem is network alignment. So this is a problem also known in the literature with different names, such as graph matching or graph reconciliation and so on. So the main problem is that I have two graphs, graph 1, graph 2, and I have to match the vertices from one graph to the vertices of the other, so that similar vertices match between the two graphs, but also the structure is preserved. So edges matches to edges on the other graph and non-edges to non-edges as much as possible. So this is the problem. And this problem has different applications from different domains. So one application comes when I do analysis of genealogy, data, and family trees. So here the setting is that I might have genealogists who have analyzed some data and have prepared different genealogical trees, and they are different researchers, and they want to combine the trees. So there is a big underlying genealogy tree, and different researchers have recovered different subparts of the tree, possible with overlap, and I want to put everything together and I form a big genealogy tree. So in that case, and this is challenging because first they might have a partial information, but there also might be noise on the data, there might be missing data and so on. Another application comes in ontology matching. So here I might have different knowledge bases and I might want to integrate them. And then a knowledge bases are represented by graph. And so then the problem of network alignment is very pertinent here as well. Also, a very interesting application is on social networks. So people join different social networks, Facebook, Twitter, and so on. LinkedIn and so on, and they have so the friends they make in one social network is very likely that they have more or less the same friends on the other, depending of course on the network and so on. So we want to match these networks and identify which user in one network correspond to the other user on the other network. And this might be very interesting, for example, for friend suggestions, if you want to make a link prediction or friend recommendation in one network. So you can get information from one and make to the other. Okay, and last application, the problem also has some task in pattern recognition. This is a classic problem on pattern recognition. So if I see a photo or a picture, I extract some landmarks, and then in order to identify the object, I want to do a graph matching with a known database of patterns, and then I can identify which object corresponds to what, and I can do my pattern identification. Okay, so this is about the motivation of the problem. So now, so how can I go about solving this problem? So this is probably you have, if you come from computer science especially, you might have seen the problem is, one particular instance of the problem is called the graph isomorphism. So I have two graphs, graph 1, graph 2. Let's say they have the same number of nodes. Is it in fact the same graph? So this is kind of a standard problem in computational complexity. It's quite interesting because it's one of these problems, one of the very few problems that we don't know if it is in P, but also we don't know if it's NP complete. So it's conjectured to be somewhere in between, to have a sub-exponential complexity. While if you consider the subgraph isomorphism, if you are looking for a subgraph and you want to identify it on a bigger graph, this problem is a standard NP-complete problem. So if we're trying to working on this problem, we are very soon realize that we stumble upon this kind of difficult complexity results and problems. Okay, but of course, a problem being NP hard or difficult has not stopped people working on that and developing efficient heuristics. So there are very different methods that most of them, of course, they find local optimum and so on. So two methods of, so what I list here on the slide, these are some of the state-of-the-art methods, and two of them that are particularly interesting for our work is the two in the middle. So Natalie and network align message passing and message passing plus plus. And I will just explain on the next slide why these two problems are interesting to us. And before I do that, I will first tell you, when I talk about graph matching, perhaps your mind also goes to a different kind of matching, which is the bipartite matching. And here I have a graph, a bipartite graph, two sets of vertices of the two sides of the bipartition, U and V. I have weights on the edges between the two sets. And my goal is to find a matching, which is a subset of edges, so that each edge is incident to at most one, and you maximize the weights of the edges. So this could, for what is shown in the picture, could be a matching, for example. As opposed to the previous problem, this is again a classic problem that we know that it's polynomial. So there is, for example, it's a classic problem in operation research. So there's the Hungarian algorithm. I can solve that in cubic time, and so on. Okay, so now, so one attempt to solve this difficult graph matching problem is by mapping it to this bipartite match problem. And these two methods that I talked before, this Natalie and the network alignment problem, they try to do exactly that. So these methods work by mapping this difficult graph matching problem, matching two graphs, into this weighted bipartite match. So the idea is to take the graphs and form a bipartite graph, so that the two set of vertices in the bipartite graph corresponds to the sets of vertices on the original graphs. And then I form my edges on this bipartite graph so that they capture the similarity between the vertices, but also structural similarity. So what I said before, that edges should match to edges on the other graph and non-edges to non-edges. And then I solve this problem on the bipartite matching. So this is one powerful heuristic that has been shown to work quite well. Okay, so this is the background. Now, what we are going to consider, the problem that we are going to study in this setting, is what we will call active network alignment. So I have the same problem. So I have two graphs, and I want to match them, to align them. But at the same time, I assume that I have some access to some human experts. So there are some people that I could ask questions. So is this node matching to that node, and so on. So the kind of our goal and the research problem we have is how do we optimally leverage this human expertise. So which questions should because these experts presumably they are very expensive, and I have to judiciously select which queries to make to these experts in order to leverage their expertise. Okay, so this is our task. For example, again, just to visualize an example, this comes from from a real data set that collected by some people in, some researchers, I think in the University of Aarhus in Denmark. They have collected different social networks, so people work in multi-level networks. So you might have, you have a bunch of friends, and you have different social networks between the friends. So for example, how they go with lunch with each other, or what is their Facebook connections and so on. And you want to identify, just by looking at this network, who is whom. Okay? And now you are allowed to make some queries. So which queries you would make? Okay, so let's listen some of your ideas. So who would you query? If I tell you, there is one expert who can tell me I can make these queries, and you can say this person is that person, how would you select your queries in order to maximize this expertise of
degree centrality? Okay,
so very good. So degree centrality. This was one idea, and what would be the motivation for that? Why would you pick that?
Because then, if you know the central node, then it's easier to identify the network, because you assume it's going to be central as well, and you know more pairs.
Okay, so I don't know if this was on the. Okay,
well, you can repeat.
Yeah, so just repeat, just for the video. So Daniele's suggestion was to pick the most central nodes. You have to be counted accountable to what you say. And the idea was that, okay, by selecting the most central, you perhaps these have more friends, so then they can help you identify other people around them. And in fact, this was a very good idea. As we'll see, it was one of our baselines. Okay. So another issue is what kind of queries you would ask. And here there are different strategies that you can consider. So one is to pick one node from one graph, one node from the other, and say, is this node the same person or not? In fact, what we are going to do is we are going to pick one node from one graph and a set of nodes on the other. So it's a set of candidates. And we will say, which node from among this set of candidates correspond to that node. And the reason for that is because this is usually, it's a relative query. So it's easier for the humans to ask this type of queries because they have context. Okay, as far as the query strategy is concerned, so one idea is already on the slides, what was mentioned, the most central. Another kind of a standard idea coming from this literature of interactive machine learning and so on is that you want to query the node that is most uncertain. All right? And this is, in fact, our approach, and this is what we will try to quantify. So what does it mean to query the most uncertain? So for example, if I have a graph here, so these are the two graphs, G1, G2. G1 has 3 nodes, G2 has 1, 2, 3, 4, 7 nodes. And somehow I know I can do some pre-processing, and I can know that node C in one graph matches node C1 and C2 in the other, and B1 and B2. So the question is, what would be my query? I would say, is B1 or B2, or A1 or A2 and A3? And in this example, you see, if you query B, if the answer is B1, then you have not learned anything, because any of C and A could go to, they have 2 options. While if your answer is from B is B2, then you have also infer where C should match and where A should match. Right? On the other hand, if you query A, if your answer is A3, then you have again perfectly determined where you should, where C and B matches. And if your answer is either A1 or A2, then okay, you have not inferred C, but you have inferred B. Okay, and so this is some of the intuition, and this is kind of the idea of trying to quantify the most uncertain node. Okay, so this is the idea that we want to query the most uncertain node. How do we formalize the idea? This now comes back to this background I was giving at the beginning. So we are going to consider methods, network alignment methods, that are based on this idea of mapping the graph matching problem to this bipartite graph matching problem. And now I'm going to do this mapping, and now instead of finding only one matching, the optimal matching, I'm going to obtain a set of near optimal matchings. Okay? And now this set of near optimal matching is going to give me a distribution, how I expect a node on one graph matches the nodes on the other graph. And I use this distribution to quantify uncertainty. So this is the idea. Okay? So this is according to this approach, so this would be the first step, the mapping of the graph matching problem to the bipartite graph matching problem. And so, kind of, okay, I will not go in details, but the technical part of our work is how do you sample near optimal matchings. And we have explored two ideas. So one is related to Monte Carlo Markov chain and Gibbs sampling, and the other is an algorithm, a combinatorial algorithm that finds exactly the top L optimal matchings. So what I said before, that the Hungarian algorithm is give you the best matching in cubic time. In fact, if you pay, if you can pay L times that complexity, you can get the top L matchings. So this is kind of an old algorithm that we kind of learned by doing this research, and it was quite useful in this setting. So in that example that I have here, so this would be your the bipartite graph on the left-hand side. They would be the one that I use for my bipartite graph matching, and then I will get the top L matchings, the top 5 in this example, and then I would form a distribution. So I would say that A in these top 5 matchings matches 40% to A1, 40% to A2, and 20% to A3, and so on for the other nodes. So I will form these distributions, and this is how I will quantify uncertainty. So now to quantify uncertainty, again, there are a few options. So the one that we found to work better is to consider, you look at the how many times a node in one graph is matched to a node in the different graph, and so the maximum of that is the certainty, how certain you are about this node. And then we consider the minimum to be the one that is the most uncertain. So it's the minimum certainty. We also consider entropy. So for me, at least, when I first thought about uncertainty and entropy, and I immediately thought about entropy, and this is something we try, but it works slightly worse than this simple approach by considering the minimum maximum. Okay. So in that example, so the proposed measure to capture certainty is, so for A1, so A, as we said before, is matched 40% to A1, 40% to A2, and 20% to A3. So the maximum is 40. And for B, the maximum is 80, and for C, the maximum is 60, so the minimum is 40. So in that case, you would pick to query A, the node A. Okay? And in that example, this is somehow intuitive. Okay, so this is some of the experiments we do. So we experiment with this idea on many different data sets. Synthetic data sets coming from the preferential attachment model, but also real social network and also genealogical networks. And kind of our strategy, our evaluation methodology was to apply this query strategy for one node at a time. So all of the different methods, all of the different query strategies make a query. You retrieve the best answer from the ground truth, and then you evaluate, you solve your network alignment problem, and then you evaluate your performance, and then you keep doing that and you keep asking queries, and after each query, you do the network alignment, and you see how your accuracy improves over time. Okay, hopefully it improves. Okay, and so these are some of the baselines. So this was the first just random. So betweenness, largest betweenness centrality is one of the centrality methods that we discussed before, and we said we are going to use as a baseline, and other methods related to the weight of this bipartite graph and different metrics of the distribution. And okay, I'm not going to give you all the results, but just an anecdote. So what we observe is, okay, so in these graphs, on the x-axis I have the number of queries. So at 0, none of these strategies, they have made any query, so they all have exactly the same precision because they use exactly the same background matching. And then as they make queries, they improve or they proceed. The accuracy proceeds in a different manner. So and by analyzing many of those on those cases, we kind of confirm the quality of the proposed approach based on the uncertainty. Okay, so conclusions, but this is not the end. Do I have 5 minutes more? Okay. So this was, I presented this idea of how one can do active alignment on network. So the idea here is that you want to leverage human experts in order to make network alignment more efficient. So the main novelty is that we view the network alignment as a bipartite graph, and then we sample matchings on this bipartite matching problem. We don't just take the top matching, and then we quantify uncertainty from the resulting distribution, and we use this uncertainty for the query strategy. And this method is a general method, so it can be worked on any kind of underlying matching algorithm that uses this idea of bipartite matching. And in particular, we experiment with Natalie and net align message passing algorithm, which is state of the art for this problem. Okay, we have so some more things that I would like to share with you is that at the beginning I mentioned that one of the motivations of the problem is when you want to match family trees and when you want to do this genealogical research. In fact, this was not just an abstract motivation, but a big part of the PhD thesis of Eric was to look at actual data from this genealogy register and make analysis of these family trees. So we work with a large data set of 10 million entries. So these are vital records that have been registered in Finland. During during 3 centuries, the data. So they start in 16th century, and they actually the data they don't stop on the 19th century. We of course obviously we have newer data, but for privacy reasons, the data stop 100 years of today, and we have birth records and marriages and burials and so on. And the task is that you want to build a family tree based on this record. So the kind of the linking problem is when you have the birth certificate of a person, you see who is the mother and who is the father, and you want to find the birth certificate of the mother and the father. So you have to solve this linking problem, and there are lots of challenges. You might have duplicate names, spelling variation, missing records, because these are very old data. People move around, and these are not digitized, so that there could be lots of errors. I'm not going into details of how of all the techniques, but as you can imagine, what I discussed before about this network alignment and multiple network alignment and entity linking was big part of this task. So we used several of these methods in order to build a complete family tree from this data, and we evaluated the resulting family tree against some ground truth data, because genealogy researchers are very active and they generate their own data. And we consider this as a ground truth, and we are able to evaluate different approaches and see how they perform. So this is this graph on the left-hand side is one subgraph of the family tree that has been reconstructed, where in this case the nodes they are colored according to different occupations. So we have peasants, crofters, laborers, and so on. And this is very interesting because you can study many different sociological phenomena that has been going over over the last century. So this is a subgraph of 2,000 nodes displaying 13 generations. So this is really quite interesting. So there are many different uses of the data and many different questions that you can do. So in fact, also in his PhD, Eric was also built a tool that people can use in order to find their own ancestors, which was also featured in a blog by Communications of ACM. So this was very nice. Okay, but one of studies that we really want to do is with respect to assortative mating. So the question is whether within different whether there is mixing between different social classes. And so, for example, it has been reported that the fact that there is not sufficient social mobility is one of the causes of income inequality. So we would like to see in our data to what extent people marry other people from different socioeconomic classes. Okay, and okay. So the questions we asked is that can we detect this phenomenon of assortative mating on our genealogy network, and does this phenomenon varies over time? Okay, so here is what we do. So we look at so in the data, of course, when two people get married, because the data is quite old, it's perhaps not so important what is the occupation of the people, because most likely they are young people, but we look what are the occupation of the parents. And now we look at the probability of when there is a marriage and two spouses get married, if their father, they have the same occupation. Okay, and so this is displayed on this graph on the left-hand side with a blue line. So we see the probability of the matchings, the percentage of the matches where the fathers have the same occupation, and we see how this varies over time. Okay, but this, in fact, this probability depends on many things, and it might also depend on the actual number of the different occupations or of the distribution. For example, if everyone in the society has the same occupation, then of course this probability is 1. So in order to have a reference model, we compare this with a null model, where the idea is that we consider people in the same region, in the same area, and we say that within we take people within 20 years, and they can marry at random to each other, and then check again what would be the percentage of the father's occupation in this null model. Okay, and so this is the orange line, and one can see that the significantly above 1. So a baseline here of 1, the ratio of the two curves would mean that there is not assortative mating, that people can marry to each other pretty much at random within the society. Okay, and this is statistically significant, and so the conclusion by this study is that so there is quite important effect of assortative mating in Finland, at least over this year. With respect to the second question, whether this varies over time, we see that there is not a significant, there is no trend like upward trend or downward trend. Okay, this is the same result where we have clustered the occupations. Instead of looking exactly at the occupations, you look at the class. So, for example, I don't know, maybe a doctor and a lawyer, they have a different occupations, but they belong to the same class. So this is what happened when you look at the class and not the occupation per se. Okay. All right. So this brings to the end of this second part of the talk, where our conclusions is that we perform a large-scale analysis of these vital records from church registers in Finland over 3 centuries. We are able to predict and to solve the to solve the entity matching problem and to build a family tree with relatively high accuracy, although this is something that I did not talk. I talk today about the problem of testing the hypothesis of assortative mating in the society over this period. And this was our finding is that assortative mating did occur in Finland over this period, but we did not find any trend whether it increases or decreases. Last point, and perhaps very interesting, is that this is an instance of longitudinal computational social science. So there are many studies today that look instances of data, of snapshots of what happened in the society today. But this is an instance that we look of how things evolve and study a data set that goes back many centuries. Okay, and as I said, most of the work was done by Erik Malmi during his PhD. External collaborators include Eva Maria Terzi, professor in Boston University. So she worked mainly on the active alignment part, and Sanjay Chavla worked on the multiple network alignment for building the family tree. Okay, so that's all. So thank you. Happy to take questions.